In this video, we will talk about terminal sliding mode controller. We have already discussed a linear sliding mode control approach in our previous video. I'll just quickly recap what is sliding mode controller. It is a type of robust control strategy which makes sure any closed loop system is robust under situation of any parameter changes or any external disturbances applied to the system. It means there is control action is not affected or it takes accordingly changes when a external disturbance or any change in internal system occurs. So what it does, a sliding mode control have a control scheme where we apply external control effort to force the system's trajectories to reach the sliding surface and to remain at that sliding surface to finally reach to their respective equilibrium points. Now we have already designed a linear sliding mode approach, but in that we cannot guarantee that it will reach in finite time. It only guarantees that reaching of equilibrium point will have asymptotically in nature, not in finite time. So for the finite time convergence, a terminal sliding mode control technique has been approached in which we use a power term to a system state, and it also improves the transient behavior of the system. But there is a consequences while using this type of approach, that is singularity problem, which is it may require infinitely large control action in order to maintain an ideal terminal sliding mode motion. So for that, a non-singular based terminal sliding mode approach is being used in this Matlab simulink example. The basic structure of terminal sliding mode control technique has been explained here, where a second order non-linear system is taken where x1 dot is equals to x2 and x2 dot is a function of system states as well as the u, that is control input. So the structure of terminal sliding surface looks like x2 plus c x1 q by p, where q by p is a power term, and where while designing a sliding surface like this, we have to make sure that this one p by q, here it is q by p, but here p by q, it should lie within this 1 to 2 range only. Now to derive control input for sliding mode approach, we need to have two parts, that is UD, that is external control effort, that is usually minus k sin s, but U equivalent is calculated by derivating this sliding surface and equating it to 0. Now for this video, we have taken example of second order non-linear dynamics where system equation is x1 dot is equals to x2 and x2 dot is x2q plus 0.1 sine function of sine 20t plus u, where u is a control input and x1 x2 are system state that needs to be reached to their respective equilibrium point. Now for designing sliding surface, we have taken x2 plus x1 3 by 5 raised to 3 by 5, and for calculating control input, we have taken minus 5 sin s as a u d part, whereas we have derivated this s dot equals to 0, and we have calculated u equivalent part, which is minus x2q and minus 0.1 sin s, which is a part of this, and saturation uf comma 3 is used because of the singularity problem present in terminal sliding mode control approach. Basically, when we derivate this sliding surface, we can get this function also, but we are taking saturation of it, so to avoid a singularity problem in our control technique. Now we will design a Matlab simulink diagram for the same system equation, sliding surface and control input, and for the reference we have linked down the reference paper in which this whole system and sliding surface and control input is presented similarly. In this section of video, we will start modeling the system equations for given sliding surface that is terminal in nature. Then we'll start developing the control input. First we'll make a subsystem for plant. Okay, so we'll start modeling this. That is x1 dot is equals to x2 and x2 dot is equals to this. So for that, first we'll take two integrators. First we'll take integrator x1, then we'll take our integrator 2. That means when we have this, when we apply a control input here, we will get x2 here with some function. So firstly we will try this. So here control input is applied. This control which is coming here is, this input is u. This we get here as x2, and this here we get is x1. So using system equations, we know x2 dot is equals to x1, and now we will, that is x1 dot is equals to x2, but x2 dot is equals to the sum function of x2 and 0.1 sine 20t plus u. So for that we'll need a sum sign. Which have three components to be added. Okay, so now we have this. Firstly u, then we have x2 cube. So for that we will need a power function here. For that we will take math function. We'll double click it and take it as power. Okay, we'll have input here as x2, and we'll apply, that is x2 cube here. So we'll take a constant and we apply here it as 3. So we have got x2 cube. While using this power function, while using this math function, we need to make sure that this signed power is always take, otherwise this program will give an error. So here it is x2 cube plus 0.1 sine t. So for that we'll take our source of sine function. This is, we'll take a sine wave, we'll apply it, which has amplitude as 0.1 and frequency at 0.5, that is 20p, and we'll supply this. So this we have got our system, which is x1 dot is equals to x2, x2 dot is x2 cube, that is x2 cube plus 0.1 sine 20t plus u. Now we'll start modeling. This is our system, or we can say it as plant. term it as plant. Now we have our system. We'll start modeling system. For that we have to make a terminal sliding surface first, which have two inputs, that is x1 and x2. So we need two outputs here. First one is x1, now system, that is x1. Now we have here as x2. Now here we have got our two outputs, x1 and x2. We will pass it through this, and the output of this will be control input, so we'll pass it this. Okay. So we have x1 here and x2. Now we know the sliding surface is x1 plus x2 plus x1 cube. So we'll take another math function in math operations. We'll take math function. Here we have we can see that is x2 plus x1 3 by 5. So x2 and here it will be x1, and we'll change it to power with signed power, and we'll take a constant, that is 3 by 5, and we'll add it. So we have got our sliding surface. We'll also plot it. And this is sliding surface. Now we have got the sliding surface. Now we will define this control input using this sliding surface, that is minus x2 cube. First we'll take this. Okay. That is minus x2 cube. So for that we'll take another math function. And that will be here. That is 3. That is minus x2 cube we have got here. That is x2 cube we have got. Now we will plot this 5.1 sin s. So if we got this, now we will have minus 5 sin s. We'll again go to math operations. We'll take sine function. Here we have got the s, so sine s into gain, that is minus 5.1. So we'll take gain and we have here as 5.1 because it is already in minus sign. And while using signal function, we have to make sure that this zero cross detection is always disabled. Now we have to make sure that this works, that is saturation of UF comma 3, where UF is this. So we'll make this one now, that is we will have x1 here, we will have x1 here, as 3 by 5 minus 1, 3 by 5 minus 1, and x2, so we'll take a product sign in math operations. So we have taken the product sign here, we have got this, and we will take x2 and we will pass it through this with gain, that is minus 3 by 5 gain, by 5, and by adding all this we get control input. So this is the block, this is the simulink diagram for basically control input. So we have got here, first we have taken the sliding surface, that is a combination of x1 and x2, that is x2 plus 3 by 5 plus x2 plus x1 raised 3 by 5, that is sliding surface. Now for the control input we have minus 5.1 sin s. So for that, as we have taken the signal function of this, pass into 5.1, and we have taken it minus, that is the first component of u, that is u equivalent, ud. Now for another component we have x2 cube minus x2 cube here, that is minus x2 cube. So we have got here, and the last part is saturation of this, minus 3 by 5 x1 raised to the power 3 by 5 minus 1 x2. So we have taken minus 3 by 5 into x2 into x1 raised to the power 3 by 5 minus 1. We have to take saturation of it. So we'll pass it through a saturation function as well. For that we will go into math function, that is saturation. It is in math operations. We have taken this So we'll change its limit to 3 and minus 3, and we will also disable these, and finally we have got the control input and we have got the sliding surface. We'll we'll take a scope now to plot all these system state as well as the sliding surface. We've taken 2 inputs here, but we'll have 3. So we'll take 3 inputs here. Now we will also plot the sliding surface. Now we will save it. Now we will run it. Because we have not defined the initial system state initial conditions. For x2 we take it as suppose 2, and for x1 we take it as minus 0.1. So when we run it now, and we see the output, we can see the output here, that is all system states that are firstly blue and yellow are the system states, and it reaches to 0, that the equilibrium point, in very less time, less than 2 seconds only. And for sliding surface we can see this is reaching phase and this is sliding phase. So this is how this control scheme work for a non-linear second order type of system. Thank you for watching this video. We'll continue this lecture in another videos.